please let me know if everything is fine, if the audio is fine. And also, please do ask questions during the talk. So I'm going to just give the talk by writing on this piece of paper. So if there are questions or requests for clarification, I'm very happy to stop and give more details, okay? So my talk will be about the AdS3 CFT2 correspondence and how integrability plays a role in it, and how TTbar deformations in particular appear in this context. And I realized that not everybody in the audience is necessarily an expert of AdS CFT integrability, or maybe of AdS3 CFT2 integrability. So even if I think that there are people that have a lot of expertise on this, I would like to give a bit of a introductory talk. So I apologize to the experts who might hear some things that they know very well, but my goal is really to keep everybody on board. So if something is not clear, it means that I'm not doing a good job and you should ask, okay? So the first thing that I would like to clarify is what observables we want to compute by using integrability. And the answer is, for the purpose of my talk, correlation functions of string states. So examples is my string worksheet. And the simplest thing that I can do to get a non-trivial object is to put two punctures, and this thing is topologically equivalent to some cylinder, which describes the propagation of a free string. So this thing will be related to some two-point function in a dual conformal field theory by means of the AdS CFT correspondence, but I will be talking mostly about the string picture. So this thing is a worksheet, which is the topology of a sphere. Other example, if I put three punctures, then I get something which has the topology of a pair of bands. So this is the string splitting, well, rather merging in this case, or splitting if I look in the other picture. And then I can go on and on. I have higher and higher point functions, like 4-point functions, etc. Right? And the thing that I want to sort of maybe call your attention to is that from the point of view of integrable theories, this object here, a cylinder, is something that we are used to studying. It's basically a quantum field theory in finite volume or finite temperature, whereas these other objects are certainly a little bit more exotic, okay? Now, I want to study strings propagating on some fixed background. And this will give some nonlinear sigma model, okay? And I was telling you that I want to study things that have to do with AdS3 and CFT2. So let me give you the background that I want to study, just to be concrete. Consider AdS3 cross S3 cross T4, okay? And in AdS3, you have a bosonic isometry algebra, which is SL2 plus SL2. This is the AdS3 part of the symmetries. In S3, you have SO4, which is of course SU2 plus SU2. And then there is the T4 part, which also plays a role, but I will not be talking that much about it for the purpose of this talk. And using a notation that I will use for the rest of the talk, we will call left and right the two copies of SL2, and also the two copies of SU2, left and right. So the reason why I call this left and right is that this is meant to be dual to a conformal filter into dimension. And these SL2 here are precisely the global part of the left and right Virasoro algebras of this two-dimensional conformal field theory, okay? In fact, the symmetries are actually given by a superalgebra. PSU 1, 1 / 2 left and PSU 1, 1 / 2 right. And this means that is a superalgebra which has an SU1, 1 part, which is basically the SL2 part, and an SU2 R symmetry algebra, and then it has 8 real supercharges, and there are as many real supercharges in the right part of the algebra. Okay, so this is sort of the picture of the theory, and what is maybe a little bit unexpected for people that are familiar with AdS5 is that this theory has lots of parameters. So there are some parameters that describe the shape of the torus. You can change a little bit the circles in the torus, and this gives you different shapes. These will not be interesting for this. And then there are basically sort of two ways of generating curvature in this background. In the supergeometry, you need to have fluxes, and there are two types of fluxes that you can have. You can have Ramond-Ramond fluxes, and the parameter is called H, or I call it H. Or you can have Neveu-Schwarz-Neveu-Schwarz fluxes, NSNS fluxes, and the parameter, I call it K. And these are sort of different ways of generating these this background. And I can have a little bit of one and a little bit of the other, or just the one, just the other. For instance, notable cases. So one notable case is you can take K equal to 0, H different from 0, and it is similar to AdS5 cross S5. So it's the case that looks more similar to AdS5 cross S5, where indeed there is no there is no Ramond field, there is no V field. Or you can have H equal to 0 and K greater than 0. In fact, K has to be quantized. And this case here is a Wess-Zumino-Witten model. It's described by a Wess-Zumino-Witten model with groups SL2 and SU2 and appropriate levels here, okay? And then you have an intermediate scenario that interpolates between the two. And the claim is that this whole parameter space can be studied by integrability. Okay, so this is sort of the claim is a claim that is certainly true at the classical level, and we believe it to be true also at the quantum level. So, so far, is it fine? Do you agree with what I'm saying, or are there some questions? Okay, if there are no questions, let me try to sketch how to describe how to compute the 2-point function. Well, really, the string spectrum string spectrum for this guy, right, is freely propagating string. This was the picture. So a sort of time and this spatial coordinate. Well, the string energy is given by a certain charge E, which is simply L0 plus L0 tilde, where this guy is in SL2 left, and this guy is in SL2 right. So this is because there is a time direction in AdS, and that's precisely the one that corresponds to this combination of Cartans of SL2 plus SL2, okay? But it is actually convenient to study this quantity, which I called H light cone, which is L0 minus J3 plus L0 tilde minus J3 tilde, where these are the SU2 Cartans. So the reason why this thing is called the light cone Hamiltonian is that if I fix light cone gauge for the string, this is the honest to God Hamiltonian of the resulting 2D quantum field theory, and I could even say integral quantum field theory. So light cone gauge, you know, is a gauge that relates time on the worldsheet to time in target space, and that's why the energy on the worldsheet, which is the Hamiltonian, becomes related to the energy in target space, which is this E. Well, shifted by some Cartan charge, but that's not particularly, is not particularly important. The other thing which is interesting in this context is that if I define H as L0 minus G3 and H tilde as L0 tilde minus G3 tilde, just representation theory tells me that these guys are actually both semi-definite positive. Is some unitarity bound is if you want the BPS bound for the unitary representation of this algebra. Okay. So this Hamiltonian is guaranteed to be non-negative, which of course is something that we like very much in a Hamiltonian. So to find the spectrum of the whole light cone Hamiltonian, I consider the S matrix, in particular the two-particle S matrix. So what's the picture here? The picture is that I had this theory in finite volume, and what I do is that I sort of cut it open by this red line, or if you want, by inserting a resolution of the identity, and I say that this thing is really a theory on the plane in infinite volume, where eventually I will sort of glue back by putting some complete set of states, right? And in particular, now I can study things like if I have some excitations in this guy here, I can try to relate it to a true S matrix in infinite volume. So this is sort of the idea. And based on this idea, a bunch of statements can be proven. So the two-particle S matrix, let's just call it as P1, P2. In this theory, there are 8 bosons and 8 fermions, so it's a 16 square by 16 square S matrix. Is almost entire fixed by symmetry. And obeys Yang-Baxter. Okay, I think I don't need to explain to this audience the importance of the Yang-Baxter equation. The exact dispersion of this model is not relativistic, but is fixed by symmetry as well. This allows, in principle, to write so-called asymptotic beta equation or Bethe-Young equation for the spectrum, and eventually TBA equations. Okay. And this gives me the spectrum of H, which in turn gives me the spectrum of the energy in AdS, because remember, this light cone energy that I had here is related to the real energy E by just this shift of this R charge. This R charge is quantized, is something very easy to keep track of. So let me tell you a little bit more about this, unless there are questions, of course. So let me start from the symmetries. The symmetries, well, I start from this algebra that I had before, PSU1,1/2, two copies, left and right, okay? And restrict to charges that commute with this light cone Hamiltonian. So I fix the gauge. This gauge breaks some of the symmetries that I have, at least manifestly, right? If you think the simplest case is strings on flat space, you start with SO1,9 and you end up with SO8 because two directions have been taken by the symmetries, and here is a similar thing.
Sorry.
Yes, there is a question.
You go ahead.
Can I ask one?
Yes. Yes.
Okay. So when you said about the exact dispersion, I'm confused one thing. So in AdS5 as well, as you know, we can completely fix dispersion, but in ABJM, also, you know, we need some interpolating function. So
yes,
some completely dependent party exists. So what happened in here AdS3 case?
I will answer. So that's a very good question about the dispersion relation. I will answer it in like 5 minutes when I get to the dispersion, if that's all right. And I will comment precisely on this, okay?
Okay.
Thank you. Thank you very much. Other questions? Okay, so I just wanted to tell you a little bit more about the symmetries. And what turns out is that from PSU1,1/2 left, let's say, what survives, we had an SU2, an SL2, and 8 supercharges, and what survives end up to be alpha of the supercharges, which I call QA, A is 1 or 2, SA, and then L0 and J3, the cartons. Same deal for PSU1,1/2, right? What survives ends up being Q tilde A, S tilde A, L0 tilde, and J tilde 3. So alpha of the supercharges survive, and they make this algebra, which is very, very simple. So it's so simple that it's actually worth writing it. So Q with S, Q with S is delta AB H. Q tilde with S tilde is delta AB H tilde, where remember this is meant to be L0 minus J3 greater or equal than 0. And this is L0 tilde minus J3 tilde, also greater or equal than 0. Okay. And then what turns out to be also true and very surprising, at least in first instance, is this is that if I take now Q with Q tilde, that actually gives me something non-trivial, some central extension C. And S with S tilde. So these two guys are central extension. So this is very strange because remember, I told you that these left and right symmetries had some interpretation as left and right symmetries of the dual CFT. And now we found out that basically there is some extension that couples the left CFT and the right CFT. This is something that is true only for states that are not physical. So this is something that people that are familiar with AdS5 will remember from the work of Beisers and others. In practice, what we have is that if we have in this picture of having an S matrix, an M particle state with particles momentum P1, Pn, the level matching constraint of string theory tells us that the total momentum is 0, but the momentum of every individual pair of particles is not 0. So in general, we want to consider states that have non-zero total momentum, that don't satisfy the physicality condition. And for these states, we will have this action here. But on the other hand, for a physical state, this is 0. The central extension is interesting because it signals something interesting in the dual CFT, which is not understood yet. And it's also interesting because it makes this algebra and the resulting coproduct, when we promote it to an Wolff algebra, very, very constraining. So I don't want to go too much into the details, but these are the ingredients that are necessary to fix the whole S matrix. And then to fix the dispersion relation, what you need is just the notion that this theory has particles that are not just in any representation, but is in short representation of this algebra that I described. And out of this, you can find that for a state of momentum P, H of P, the energy, takes this form. And I will first write it and then tell you what it means. So here, this K here is related to the Wess-Zumino-Witten level, was one of the two parameters that we had before. This is related to the Ramond-Ramond flux. This mu here, it identifies the particle species and it runs over the integer. So in practice, we can have particles with mu equals 0, 1, 2, 3, 4, 5, or -1, -2, etc. And these other parameters are given. So an interesting thing is that K is quantized. So it's completely unambiguous what it is. Once identified, let's say, in the semi-classical theory, I know exactly what is meant to be at all loops because it cannot change. Whereas this H here is something that can be related in a non-trivial way to the coupling constant of whatever is the dual conformal field theory. Okay, and that I hope answered the question. So in this sense, this coupling constant is like the coupling constant of ABJM. It's not completely clear how to relate it to the coupling constant of AdS4. It's not completely clear how to relate it to the semi-classical coupling constant. It will be some non-trivial function of it, okay? This is just something that comes out of representation theory. The other thing that I want to stress is that for none of these theories, with the exception of a very special setup, which is K equal 1 and H equals 0, but for none of these theories, the dual theory is known, okay? So using integrability is crucial to try to understand what the dual might be. Now, let's have a quick look at what can happen for this theory, and then I will tell you something about the relation with TTbar deformations, okay, which I've advertised. I told you that you can tune all these parameters. So the first thing that you notice is that for generic value, so K and H generic, I have to consider the various value of mu, and in particular for mu equals 0, I have no mass gap. Okay. So H of P, in the case in which mu equals 0, which is one particular species of particle, is just k square over 4 pi square, p square plus 4h square sine square over p of p over 2. So for small momentum, this guy here has a dispersion that, roughly speaking, looks something like this, okay? And here it has a cusp. So here it looks a little bit like a relativistic theory. So this is P and this is H. These are the massless modes of this theory, which are a little bit of a puzzle if you think of integrable theories and integrable theories and in general theories in 2 dimensions. The other thing that you can do is that you can just take k equal to 0 and then h of p is square root of mu square plus 4h square sine square of p over 2. This looks very much like AdS5 for people that are familiar with it, only that now mu can also be equal to 0. If not, this would look like the bound state number of AdS5, okay? And for h equal to 0, it's actually much more interesting because something even more drastic happens. You see all this piece drops out and you're left with the square root of a square. So h of p is just the absolute value of k over 2 pi p plus mu. So this is a theory of particles that move at the speed of light, either to the left or to the right. So this theory looks like the most bizarre, if you want, because it's a completely massless theory. Even it's not entirely relativistic, but you know, it's almost relativistic. This thing is just a little shift. And for this theory, scattering is extremely simple. Because you see, the velocity of these particles, as I was saying.
What's the value of the coupling to make H to be 0?
Sorry?
What's the value of the coupling which makes H to be 0?
The value of the Toft coupling, what? I didn't quite get the question again, sorry.
H should be a function of lambda.
So there is, so I don't know what the Toft coupling, because I don't know what the Toft coupling is, because I don't know what is the dual theory of this model.
Of the level divided by n, and the n goes infinite.
So there is no, so what I can tell, well, I can tell you what this k is in terms of, for instance, the NS5 brains and things like that, but there is no dual gauge theory for it.
So in this AdS3 CFT2 duality,
yes.
CFT2 side is a tensor product of a certain two-dimensional conformity.
Ah, very good. Okay, so
And then
there is a statement that the dual CFT is related to the symmetric product orbifold of n copies of a free theory essentially, and this statement is exact for k equals to 1 and h equal to 0. So if I put k equal to 1, then I know what the dual is, and this is the symmetric product orbifold. For generic k, it's meant to be some symmetric product orbifold. There are some proposals, but there is basically no understanding of what the dual is. So I cannot really tell you what k is in the dual theory because nobody knows, honestly speaking, what is the dual theory. Only for k equal to 1, people know it. So it's very, very different from n equal 4 superior means. That's part of the mystery, if you want, of this theory.
So you are mainly focusing on string side in this question.
Yeah, so on the string side, everything is sort of under control. I have these parameters, but what the dual might be is not clear.
What's the physical meaning of H?
Sorry, the minimum of H?
Physical meaning of H.
The meaning of H, okay. In string theory, what you can do is that you can start from this background. This background is generated by NS brains and fundamental strings. And then you can switch on certain moduli. And in particular, there is some modulus that corresponds to a scalar, a Ramond-Ramond scalar charge. And this thing corresponds to some marginal deformation in the dual theory, presumably. And this marginal deformation corresponds to switching on H. So H, you can really think, for any given value of K, you can think of turning on some marginal deformation in the CFT that relates to turning on H. Okay. K is, instead can only change discontinuously, so it's a bit of a, it's not really a modulus, it's more like a parameter. Okay. You can see some hint of the fact that there is some sense also in integrability for K being integer, because you see that K is integer, mu is integer. Here I have a 2 pi, and when I shift P by 2 pi, it's like shifting mu. So there is some nice interplay between the sort of representation that you can get here and the fact that they basically go on to themselves up to shifting P by 2 pi, and the fact that K and mu are both integer. So another thing that I wanted to say is that the velocity, which is dH over dP, is just plus minus K over 2 pi. Okay, so these guys move with the speed of light either to the left or to the right. And it seems only reasonable to say that, so we say, let me just say that I write again here dH over dP, which is the velocity. This is equal to either plus K over 2 pi or minus K over 2 pi. And I call these guys chiral. And I call these guys anti-chiral. Okay, just because the one moves to the left, one moves to the right on the worksheet. And it seems just natural to say that S matrix between chiral is just trivial, because it doesn't really make sense that much to scatter two things that move exactly in the same way, okay, with the same speed. Interestingly, if you take the limit of the S matrix that you find for general parameters, you try to take this limit, you get something non-proportional to the identity, but it's something non-perturbative whose meaning is not completely clear. And then the only thing that sort of makes sense is to consider S, I guess, chiral, anti-chiral, where I have a particle that moves. So in my in state, I have a particle that moves like this and a particle that moves like that. And those could scatter. And then I write down SP1, P2. And it turns out that this S matrix is extremely simple. It takes this form. It's proportional to the identity. It's not the identity. And the proportionality factor is something that will be well familiar to those of you that work on TTbar deformations, because it's just this function here. So-called Toft-Drey shockwave S matrix. This is just the Mandelstam variable S for massless particles, and this is just your coupling.
Alessandro?
Yes.
Hi, it's Matthias. Just a question.
Hi, Matthias.
There's a question. So your argument about S chiral being one, I mean, I can believe that it's one, but you somehow said because they are moving in the same direction, there can be no scattering. But that I don't understand, because like one could, I mean, one excitation can just take over the other. Or...
Well, they are moving in the same direction with the same speed. You see, in this theory, the speed is independent of the momentum.
Okay.
So that's sort of what makes it a little bit tricky. Yeah.
So I mean, because they're in the same direction and because the speed is the same. Okay,
yeah. Same direction, and so the speed is constant in this theory, essentially. They're really relativistic massless particles at this point. But in a sense, the concern that Matthias had is a good concern, because it's not completely clear whether this thing, which is strictly speaking an assumption, whether it's entirely justified. Certainly, if I take the Lagrangian, for instance, on the worksheet and I do perturbative calculation, I will never be able to do a perturbative calculation and gives me something here, just because of how perturbation theory is defined. Essentially, you have to solve some momentum conservation delta functions and energy conservation that gives you only trivial results. But you might wonder whether something non-trivial can happen, right? Because there are these study by Zamologikov and others of massless theories, and sometimes you can find non-trivial things even in this sector. So the reason to yeah.
Kind of contact terms or something like that. So it's almost one, but somehow it's there on top.
So there was a study of massless matrix which are obtained as limits of massive ones, and in some cases you can find non-trivial answers. These appear, for instance, in flows between conformal field theories, most notably. But here we have an advantage, because we know that this theory is also a Wess-Zumino-Witten model. So a Wess-Zumino-Witten model on the worksheet is a theory which can be studied in perfect detail. I mean, it's a conformal field theory, and among conformal field theories is among the simplest in a sense. So you can study the spectrum, and the spectrum is actually known. And even more shocking, maybe for people that have worked for several years on AdS5, the spectrum is known as in closed form with respect to AdS5, where of course, just writing the energy of a single, like say Konishi state, is an extremely difficult exercise. Here you can write the spectrum of any state in closed form, and it's basically given by some square root, pretty much like for flat space strings. It's not exactly the same thing, but it's very closely related. There are some subtleties that have to do with the existence of spectrally flowed representation and other type of representation for the Wess-Zumino-Witten model, which I don't have time to discuss. But still, taking care of all of this spectrum is known in closed form. And what can be proven is that this S matrix, this very simple S matrix, also gives a spectrum that can be expressed in closed form. This is true even if one does everything very properly and does the mirror TBA for this theory. So even accounting for wrapping interactions, the theory has still a spectrum that can be written in closed form, and the spectrum precisely matches. Okay. So it matches the integrability construction. So this is, if you want, a posteriori validation for this very simple S matrix. Now, this S matrix, and I think we started a little bit late, but probably I should start wrapping up. So this S matrix, to me, is very interesting for a number of reasons. One is that it's very reminiscent of the simple S matrix of a TTbar deformation of a free theory. It's not exactly a TTbar deformation of a free theory, because here the dispersion that we had was a little bit different. So I remind you that we had this dispersion, which was shifted by this mu here. Nonetheless, it's very interesting that it's just so simple and of the TTbar type. And the other thing that is interesting is that since the theory is so simple and it admits a very simple treatment of the spectrum, the question is whether we can also have a similarly simple treatment of 3-point functions and 4-point functions. Again, there is a way to compute them by CFT techniques, but the question is whether we can use integrability techniques to compute them. And the motivation is that there is an integrability approach, the so-called hexagon formalism, to correlation functions, but we don't understand it very completely, I think it's fair to say, especially for what has to do with the finite volume corrections. So the question is, can this setup be a playground, if you want, for hexagon correlators? And that's what I want to briefly and qualitatively discuss in the last 5 minutes of my talk, okay? And the answer to me is yes, but I think the question is very much open, but I'm very confident that the answer will be yes. So let me just give a little bit of a flavor of what we are talking about. So what we are talking about was this 3-point function, this pair of pans topology. And the idea of this hexagon approach is to sort of cut open, like we did for the worksheet, this object by cutting along the red lines. And what we get now are two disconnected patches. And each patch has 6 distinct edges. And that's why this is called the hexagon formally, because you are studying objects with 6 distinct edges. And the other step, the even further step, is that this object here can be related somehow to an ordinary theory where I inserted some non-local operator. So this non-local operator is exactly some conical excess operator, if you want. If I call my edges 0, 1, and 2, this would be 1, this would be 2, and sort of this would be 0. And the idea is that now I can talk about things like, if I have an operator that goes from 0 to 2, sorry, an excitation that goes from 0 to 2, a particle of momentum p, this is like having this operator emit a particle, or vice versa, something like this would be this operator absorbing a particle. And therefore, what I want to study are form factors of this theory. And what is very interesting is that just like in AdS5, you have enough symmetry to completely determine these form factors. So if I call this hexagon operator O, I guess I called it, and we want O with P1, P2, Pn. And it is possible to do it by symmetry. So I don't have that much time to go into the details and justify this. I just want to write down for the experts the form of these symmetries, because it's very reminiscent of what you have in AdS5. So in terms of this algebra with the generators Q and S and so on and so forth, now here we have, again, half of the, yes.
I have a question. So is
Oh, yes.
cross, when you fix this phase factor of the scattering matrix, you get some kind of crossing symmetry for variability?
Yes.
So what are they?
So I didn't discuss this in detail because of time, but the symmetry arguments fixes the S matrix up to a prefactor, the dressing factor. There are crossing equations for the dressing factors. And there are also, in some cases, proposals for a solution of the dressing factor. In the case that I was discussing, the simple case here, you see that the whole S matrix is just a CDD factor. This thing is a solution of the homogeneous crossing equation by itself.
So the crossing are changing to some other value?
Crossing would very simply send P2 minus P in this case.
Ah, okay. So, thanks.
More questions? So I just wanted to give a little bit of an idea of what sort of charges one would have. I might have written the indices in the wrong way, but it doesn't really matter. They are raised and lowered by some SU2 anyway. So you see that morally, the charges that we have are sort of half of the ones that we had before, and it's some sort of diagonal combination, funny diagonal combination of Q's and S's, which is a bit unnatural because Q and S's used to be, like morally one was conjugate to the other. But this is actually, for people that are experts in AdS5, is actually very similar structure to what you have there. I don't want to insist on this for people that are not familiar with this. Unfortunately, I will not have time to explain it. What I want to stress is that this gives a working or workable hexagon formalism for this theory. And we can make a test, which is check the correlations of BPS operators. So let me just say this thing with just a little bit more detail, because people that are familiar with AdS5 might be a little bit confused just now. So in AdS5, we know very well that there is a, in AdS5 cross S5, there is one half BPS multiplet with given R charge J, okay? And morally is the guy whose IAS state is trace Z to the J. So it's very trivial in a sense, the structure of BPS operators. Here, we can instead of giving just J, the R charge, we can give J and J tilde, right? The SU2 left and the SU2 right R charge. And the question is, how many multiplets with a given value of J and J tilde are there in this theory? Okay. Or for instance, another question is, can I take any J or J and J tilde? Well, it turns out that the answer is known and is actually rather simple, but not trivial. So if in this notation where I have J and J tilde, I have one multiplet where J and J tilde are equal and half integer. There is one such multiplet. And then I can construct more multiplets. There is one multiplet where I increase by 1/2 J, but not J tilde. And that actually are two multiplets. There are two such multiplets I can construct. Or clearly by symmetry, you can, even if you don't know the construction, you can imagine it by symmetry. I can do the same here. So already, instead of having just one multiplet, here I have these new multiplets, one, and then these two and these two. But it goes on, and I can also increase this guy even more. So this is the highest weight state of the charge of the highest weight state of the multiplet. Or I can increase this guy. And like this, I have 4 such multiplets. And so on, okay? So for people that are familiar with this sort of thing, this looks like very much like a Clifford module. Well, it will look like a Clifford module once I will have finished writing it. It consists in total of 16 multiplets. For any value of n, you have 16 multiplets that you can write down. So when I consider the 3-point function of protected operator, is a simple object, but you see there are a bunch of choices that I can take for these protected operators, right? And some of them are a little bit tricky, because if I look at a state with the, I don't know, charge of the highest weight state 7/2, 7/2, I can get it from this guy with n equals 7, from any of these 4 guys with n equals 6, or for this guy with n equals 5. So you see that all this column mixes with itself, all this column mixes with itself, and all of this column mixes with itself for different values of n. It's only these guys they don't mix. I call this guy v plus and v minus n, and v plus n does not, or also plus minus, does not mix. So because of that, these are the simplest states to study, the simplest multiplets. Otherwise, even if the result for the 3-point function is known, you wouldn't know exactly which multiplet you're computing. And what you can compute essentially is, you know, a 3-point function like this. And 1, and 2, and 3. Okay? Or you can compute a 3-point function like this. Where I put a minus sign here. And there are two more that I can write, but you see, there will be the one with all minus, which is sort of related simply to the one with all pluses, and there is the one with 2 minuses and 1 plus, which will be related to this one. So if I want to simplify my life even a bit, I just take the ratio of these two guys, so I get rid of any problem with normalizations. And the answer is known by Wess-Zumino-Witten calculations and other type of calculations, supergravity calculations. And it looks like this. Okay, so it's a fairly simple but still non-trivial function of n1, n2, and n3, and that's exactly what we have verified. Okay, that was our check. This 3-point functions is constant all over the moduli, the parameter space of the theory, so it's protected itself. So it's very easy in a sense to test it. We would like now to go and test other quantities, but there are no predictions for most of them. So what we need to do, what we want to do essentially, is now to take all these formulas, which we developed in general based on symmetry arguments and so on, and extrapolate it to the Wess-Zumino-Witten point to compare it with the construction of the Wess-Zumino-Witten point, and to also understand better this hexagon formalism. And the last thing that I say is that since we are computing form factors, this might actually, hopefully, shed some light on the complicated question of studying form factors in TTbar deform theories. Because I told you that this theory is sort of a simple TTbar deformation, and we are studying some form factors. So hopefully, by studying this concrete example, we might learn something about the more general question of constructing form factors of TTbar deform theories. So I think now I should stop and leave time for questions.
Well, I have one question now. So you didn't show the formulas for the form factors, but for correlation functions, you have to sum over all multi-particle form factors to get a correlation function. I mean, in massive theories, this converges pretty rapidly, but does this converge here? I mean, does it converge pretty rapidly? I mean, suppose you want to do it numerically, how many particles do you need in your intermediate states?
In this case here, because of essentially supersymmetry and the fact that these quantities are protected, essentially all the effects due to so in this construction, what you're saying manifests itself as sort of more like finite volume corrections, I would say, in this context, a little bit different from the usual form factor construction. But for this particular guys, everything sort of trivializes. It's extremely simple. Now,
but maybe it's only because looking at the ratio. I mean, if you weren't looking at the ratio,
no, it's more because these quantities are protected. If there is some cancellation order by order, I mean, term by term, a lot of terms are zero because of cancellation between fermions and bosons. It's a supersymmetry statement at this level. Now, for the general theory, when we have massless modes, I think it will be very difficult to understand it. I think there will be some that is where I expect to encounter some obstacle. For the particular point in which we go to this Wess-Zumino-Witten point, I hope, I'm not sure, but I hope that some similar cancellation as what was observed here will also be observed, because I know that the result is meant to be extremely simple and extremely constrained by basically smoothie symmetries and things like that. But I don't know yet how that happens. But the hope is that there will be some cancellations. Otherwise, I agree that when you have masters guys, it will be very difficult calculation.
Mm-hmm.
Okay.
Alessandro, can we talk for a second about this dual? I mean, you always said the dual is not known. Now, my question is it obvious, or two questions? Is it obvious that there should be a dual? And if so, is it obvious that it should be a complete series?
So I think that there is an expectation that the dual should be a conformal field theory in two dimensions. There are some arguments that are based on some constructions, some string theoretical constructions where one cooks up some Yang-Mills theory that has a scale in two dimensions. The Yang-Mills theory would have a scale, but flows to some non-trivial conformal field theory in the infrared, and that's meant to be the dual. Now, this
obvious that there is a dual at all. I mean, like, or is it just based on the fact that in many similar cases there has, you know, that
there are some constructions that sort of, you know, by qualitative study of the RG flow of this massive Yang-Mills theory, there is an expectation that this should be a non-trivial theory as opposed to, you know, like the trivial theory, the empty theory, or no theory at all. Now, there is one proposal for, so k equal 1, h equals 0, the dual is known. I think it's beyond doubt. So k greater than 1 and h equals 0, there is a proposal in terms of symmetric product orbifold of Liouville theories. But this proposal misses, I mean, it reproduces some of the features of the theory, but not all of them. So it's a bit it's interesting that you have a theory that reproduces in particular part of the spectrum, but not all of the spectrum. And it's a bit funny because, of course, well, I don't want to enter too much into the details of the spectrum of this theory, but there are two sectors, so-called long string sector and short string sectors. And this proposal is okay for long strings, but not for short strings. Short strings include all the BPS states of the theory. And short string and long strings, they are not to decoupled sectors, 3-point functions and so on couple them. So nobody knows, okay? I believe that there should be a way to sort of to incorporate the whole, to find, you know, to adjust this proposal in order to have the correct thing, but how this should be done is unknown.
Okay, thanks.
Okay, Alessandro, since we are far behind the schedule, we can do this question after the second speaker's second talk. Okay, we have some free time.
Also a bit of time tonight.
Yeah, also, yes. Yeah. Okay, let's thank
great job.
So, Tiago, are you there?
Hi, I'm here. Can you hear me?
Yeah, yes, we can. But we will start the recording first, and then we come back. Just wait.